Hi everybody. This video is on the principle of least action. Now this is the main topic for chapter 7 in our book. So this is another way of doing mechanics instead of the Newtonian mechanics that we're used to. We're going to call this Lagrangian mechanics, and it's based on this principle of least action. So the principle of least action, I'll get into further as we go, is the idea that there is something minimized as a particle traverses from one point in space to another point in space. And what is minimized is what is called by physicists the action. So this was first proposed by Pierre-Louis Maupertuis, and he was a French mathematician. For a while, he was president of the Prussian Academy of Sciences when Euler was the director of mathematics there. But when he proposed this principle of least action, it was not very precise, it was very vague and really not useful. So it was put in a useful form, precise form, by Joseph Lagrange, another French mathematician. Famous, you've heard of Lagrange's name, I'm sure. So we're going to develop what's called the functional called the Lagrangian. And Lagrange, although he's a French mathematician, he became director of the mathematics at the Prussian Academy of Sciences for about 20 years when Euler retired, and or when Euler left that position. He eventually, when he was 51, moved back to France and stayed there the rest of his life. So the principle of least action is the idea. We're going to develop something called the Lagrangian, and then we use Euler's equation, but the functional that we use is the Lagrangian, so we call it Lagrange's equation. Sometimes it's called the Euler-Lagrange equation. Okay. So to get started, I want to remind you of Euler's equation. So we had some integral that we want to minimize, and we found that this integral, which we call functional here, one of the conditions that we must satisfy to minimize it is Euler's equation here. So this functional is a function, we're saying, of the dependent variables y and y prime, the derivative of y, and the independent variables x. So this was Euler's equation. We derived that. So in the late 1700s, early 1800s, again, we were thinking of, is there something in nature that's minimized that will give us the actual path of a particle? And what I'm going to show you today is that thing that we would like to minimize is called the action. And it can be written like this, and we'll use S for the action. L is our functional in here, and this is called the Lagrangian. So and now I'm writing it as the independent variable as t for time instead of position. And if that's so, then to minimize this, we'll use Euler's equations, but since we have L here, we'll call it Lagrange's equation. And the reason we'll call it Lagrange's equation is that Lagrange was the first one to apply this to the movement of particles. So what I'm going to do in this lecture, this is a derivation lecture, I'm going to actually show you that for a conservative force, this is equivalent to Newton's law of motion. F equals ma. So we're going to talk more about what this is, and then I'm going to show you that Lagrange's equation is equivalent to F equals ma. And then in the next videos, we'll apply Lagrange's equation. So this is called the Lagrangian method. instead of the Newtonian method of physics. So the action is going to be the sum over a bunch of infinitesimally small paths, this relationship, the kinetic energy minus the potential energy. So we add them up, so we have an integration here. This is the action. And what we're stating is that the path the particle actually takes, y as a function of time, is going to be such that it minimizes the action. So again, that means what we're going to call the Lagrangian is the kinetic energy minus the potential energy. So just like before, so let's say this is our y of t, this is the actual path that will minimize s. And this path here is going to be, I'm going to call it underscore y underscore of t. And this is simply the actual path plus, again, our deviation. From the path. Where alpha is some constant. So let me take a minute to talk about some notation that we're going to use. From time 1 to time 2, if our path that's not actually the true path, the path that we try here, is different, we call that difference the variance. We use this notation. I'll use delta y. So that's the variance. Now it's different than using dy, what we call the differential, because this is actually written as if we were looking at time. So a differential is if you start here and maybe your true path's here, but you take, maybe I should have gone like this. You take the slope here over time and you find where you would be, how much you went up this way, dy. So that's a linear, this is a slope. So you start at t1, you go up linearly. Here, this is really this area under this whole curve here. So the area that designates from the true path, your imagined path here. So this is what we call the variance. So pretty soon I'm going to use that notation. I want you to understand what I'm talking about. Okay, so y of t is the true path. Y underscore. This is, if you want to call the fake path. It's not the true path. It minimizes the action. So S is action of true path. And this is action of, I guess, what I'm calling the fake path. It's not really a good word to use for that. The untrue path, our example path, if you want. But for now, I'll call it the fake path. So, we're trying to find the path that will minimize S, the action. Now, just in general, when you're trying to find minimas, let's say, for example, we have a temperature as a function of position, if you will. And maybe the temperature goes like this. So around the minimum here, around the minimum, the temperature, you can usually fit that with a quadratic, so the change in temperature is proportional to delta x squared around minimum. When you get farther out here, it might be proportional just linearly with change in x. But around the minimum, it's proportional to delta x squared, a quadratic. So why am I bringing that up? It's because when we're trying to minimize s, that when we're around the minimum of whatever s is, it's going to be, the change is going to be proportional to our deviation. So to say that again, what I mean is the change in, well, I'm going to look at, of course, I'm looking at my fake path, so I'm looking at the action of the fake path, so I guess I put a line under there. The, excuse me, the difference in it from the true path ought to be proportional to the deviation squared when I'm close to the minimum. So what that's going to mean is when I look at this, the action of my fake path, when I get around the minimum, the stuff that goes first order to the deviation ought to be 0. So let's look at the action for the alternate path. It would be T1 and T2. Kinetic energy will be written for this path. The velocity is dy underscore dt squared. Because y underscored is the alternate, y underscored is the alternate path. I'm just going to leave out the alpha and write n of t. Minus the potential energy, minus the potential energy, I'll just write that as v of, now that's usually a function of position. Okay. Now what I'm going to do is replace dy underscore dt with dy dt, the actual velocity, or the time derivative of the actual path. Then I have also this plus. So when I stick that in here, I get this is equal to I have to square that, then plus the potential energy, and instead of, I guess I should have put up here this potential energy, that should have been an underscore for this position. That's the alternate path. So now I replace that with So to let you know where I'm going with this is I'm going to try to write the action of our alternate path as action plus of the true path plus some linear terms plus higher order terms. And what I mean higher order in the n here, the deviation from the true path. And we're going to set these to 0. The linear component, and see what happens. So when we look at the deviation from the true action. So that's where I'm going. So now I'm going to rewrite this as T1 T2 1/2 m, and then excuse me, this will become dy dt squared plus 2 dy dt dn dt plus dn dt squared. So that's what this becomes. And now I'm also going to expand this. Or I should say I'm going to write this as an expansion about y where n is 0. So I'd write that as this plus the derivative times n, and then plus I would go to higher order nn. So when I stick, oh, I'm sorry, I see a mistake up here. That should be a minus sign, by the way. So I'm going to put that in here. It's the higher order stuff. So now I have my action from my alternate path here written like this. Now what I'm going to do is, since I think around the minimum, if I want to minimize this, it's going to depend on the deviation of t to the second order. So I want to write this integral here in the form where I have maybe part of it to the first order and n part, and then second order and higher on up. So if you look, I have the action is this. I have T1, T2, 1/2 m dy dt squared. So that's the kinetic energy, and that y is the actual path. And if I put minus v of y here, and I do this part, this integral, that's the actual action for the true path. And then what do I have left? I have plus T1 to T2, 1/2 m, and then I have 2 dy dt dn dt, and then minus v prime y times n. So that's all the first order stuff. And then I have the rest of this minus on our second order and higher. Okay. Now, I said, well, let me rewrite this first. The action of our alternative path is equal to the action of the true path, that's this part, plus then the first order deviation would be this. 1/2 and a 2 cancel. I have m dy dt dn dt minus v prime y times n dt plus the second order and higher stuff. Okay. So what we said is once we get around the minimum, that the variance in S should be second order and higher, and that the first order stuff should be 0. So we're going to say the variance to first order should be equal to 0. So that's what we're going to try to do. Now, when we want to do this now, realize that what this n is, I didn't write it as a function of time because I'm lazy here, but y of t is our alternate path, our fake path we called it. It's equal to the true path plus this. So this is not necessarily 0. So what I would like to write is this variance to first order as an integral of stuff here times n of t dt. And then if this is going to be 0, I would know what is in here must be 0 since n of t is not necessarily 0. So that's what I'm going to do. So I'm going to go back up here. I'm going to rewrite this part. So how can I rewrite that? Okay. So I want to rewrite this, and I'm leaving this blank. So if I take this and I write n of t here, and then my m dy dt. If I took the derivative of this, what would that be? It would be n times, I'd have m d squared y dt squared plus m dy dt times dn dt. And this is what I have right now. So evidently I can rewrite this as this minus okay. So what does that mean? That means this, that this part of the integral can be written as, when I do the integral of this, I'm going to get minus t1, t2 Now, I want you to remember we said here's the true path, here's t1, here's t2, time, and here is the fake path. What we require is at the endpoints, t1 and t2, the deviation part should be 0. It should match the actual. So what this is going to mean is that's going to be 0. So going back to our variance in first order that we want to be equal to 0, it should equal t1 to t2 negative n of t m d squared y dt squared minus v prime y n dt. So I can rewrite that, of course, as pull out the negative sign, t1, t2, m d squared y dt squared plus v prime of y n of t dt. And I want that to be 0. So what does this tell us? So this must be 0 in here. I want that must be 0. This is the acceleration, right? ma plus, and then this is the derivative of the potential with respect to y in this case is 0. So we get ma is negative the gradient of the potential. And this was supposed to be for a conservative force. So for a conservative force, this is exactly Newton's law of motion. Okay? So if we minimize our variance, to first order, we get basically Newton's law of motion. So let me clarify what we were doing. So what we did is we said, look, if we have our fake path, we have an action for that, and we have an action for the true path, and towards the minimum of the actual action, the variance in these two first orders should go to 0. So, and in fact, if that happened, then we showed we get, for our conservative force, say we're in one dimension, we have Newton's second law for a conservative force. Now, so what this shows also, if you think about it, is that minimizing the action leads to Newton's law, Newton's second law here. Now, this was for a conservative force, but what you need to realize is that all of our fundamental forces are conservative forces. So when you get deep down at the deepest level of physics, there's really no non-conservative force. These non-conservative forces only arise because of our inability to handle problems at the macroscopic level when we have many, many particles. So that's how non-conservative forces arise. So Richard Feynman said that all the fundamental laws of physics should be able to be written in terms of least action, minimizing the action. So we call that to minimize the action S. We call that the principle of least action. So what I'm going to show you next is that if we're going to minimize the action, then one of the requirements is we have an Euler equation where this, we use this as our functional L. It'll be a function of y, derivative of y with respect to time and time. So that's next. Okay, so we showed that because the variance in our action between the fake path and the real path, if you want, look like this. This is n. And this had to be, since it was first order in n, this is supposed to be n here. It had to be 0, so what's in here had to be 0. So now I want to show you that that's equivalent to saying that this is Euler's equation, but we have for our functional here the Lagrangian here. So I want to show that this is equivalent to that. Where L, in this case, is 1/2 m y dot squared minus the potential. In this case is a function of y. So the partial of L with respect to y is just prime of y. Oh, I'm sorry, it's negative because of the negative sign there. And then we have partial of L with respect to y dot. Well, that's just m y dot. And then if I take the derivative with respect to time of that, that's m y double dot, which is the acceleration. So then I have this equation dl dy minus this is equal to negative the potential, derivative of the potential, minus my double dot. And if that's equal to 0, then we have my double dot is negative the gradient of the potential. So what we're going to do and then now is to take this equation. Now we don't call it Euler's equation anymore. We'll call it Lagrange's equation again, because Lagrange was the one that actually applied it to a particle motion. And we'll see what we can do with that, what kind of problems we can do. So that's going to be the next videos.